It's been a fantastic week, I know. So I think today is going to be a bit more relaxed, hopefully. Hopefully you are still with energy. I hope so, because actually what we are going to see today is quite relevant, which is how you connect all the things we have been seeing through the week to observations. And we will see some of the basics of data analysis, which are, of course, essential. But just to, as always, to see where we left things, we have been working hard to get to the derivation of what is the gravitational wave signal that we observe from the coalescence of compact binaries that have traveled through the universe. And some of this has already been brought up again during the Q&A session, but let me just write everything for consistency. We've seen that one of the main observables from the gravitational wave signal is that we get the information of the luminosity distance, which is interesting because this encodes, of course, information about the expansion rate of the universe. And we've seen that because of the redshifting of the gravitational waves, we are sensitive to the detector frame masses only, which also includes some information of redshift. And then we also saw the other day that from the arrival time of the gravitational waves at the different detectors on Earth, we can get some information on where they are coming in the sky. And we define, broadly speaking, three and the very first fact is that from the notion that we know the shape of the waveforms, and that from this amplitude we are extracting directly a measurement of distance. This is why gravitational waves are referred as standard sirens. And then there are different flavors for the different standard sirens. The three main ones that we are making use of today, although others already were brought up as well, like when you include tidal deformability effects. But the first one is when you have an electromagnetic counterpart. And we were seeing that case is mostly when you have the coalescence of two binary neutron stars. And then there were two elements. One is that there would be a jet of a short gamma ray burst. And then the other is that there will be emission of afterglow, which is referred as called kilonova, and short gamma ray burst. And actually today, later, I will show you some plots on projections in terms of what is what can do with bright sirens, depending if one looks for one or the other. But the main idea here is that you get from the EM, you get the redshift of the host galaxy. But we also learned that this is rare. So you can also say, okay, we have some sky localization, we have some error in the distance. So this gives us some localization volume. And then we can say, okay, in this localization volume, I have this fantastic galaxy catalog that has all these galaxies. So then my gravitational waves should come from one of the galaxies within this localization error. So here, the redshift is statistically inferred from all the galaxies in the localization error. Sorry, localization. error. This is great because this is a method that you don't need to have a direct electromagnetic counterpart and therefore can be used, for example, for binary black holes. The difficulty is that, as we have learned as well, and we will see also some examples, the localization errors that we have are not the best, are of the order of tens when we have very good measurements, if not 100, if not thousands of square degrees. And of course, that's a really large fraction of the sky. So it's difficult to do it. But as we increase enlarge the network of detectors on Earth, this localization will improve. And also, hopefully, with new galaxy surveys, the catalogs will be more complete at higher redshift, and then one could use that. And then finally, the last method that I highlighted, and then you should ask questions if you have, is what I refer as the spectral siren method, which essentially does not make use of any of external information and just makes use of the fact that despite the fact that an individual gravitational wave does not contain information of the redshift in the masses because it's degenerate with the source mass, if you if the distribution of masses has some features, and we will see actually what are those features from the data, then as you change if you look at this at some luminosity distance 1, and then you look at this spectrum at some other luminosity distance DL2, which is larger, then how much the whole spectrum is shifted will encode some information on the redshift. This is the toy model explanation. The way to actually do the analysis is what is known as a hierarchical Bayesian inference, in which from the observations you infer the parameters that are describing the whole population. And you do it simultaneously for your mass spectrum and the cosmological parameters. Are there questions about the three sirens? Yes. Yes. So this is, sorry, I realize that every time that I explain in this very toy example, I make you all a bit more confused. So in reality, we just take all of the events, and each event is at a different luminosity distance. But then what you do is that you don't only model so this is the distribution of the sources in mass, but we also, so in this hierarchical inference, we model this, the distribution in mass, but we also model the distribution in redshift. And we also have H of C. So essentially what you are doing is you are fitting for all of these things simultaneously. And if you change the merger rate history, that is going to be degenerate with changing some of the cosmological parameters in the same way that if you change the mass spectrum, this is going to be degenerate. So this is also already gives you a sense as well that perhaps there are many degeneracies here, and this is also why this is a method that is most effective when you have many events. Because when you have many events, actually it's only then when you can disentangle these two things. But, and we will see results from current data, but at the moment, this is, of the order of, I think, at least 15% errors in H of C that we are measuring at a redshift of, I think, around 0.5 or so, sorry, 0.5. So it's not a super precise thing at the moment, but that's because we only have 100 events. If you have 10,000 events, then you can do much better. I don't know if there was another question I thought I saw, but maybe not. Is there other questions for the sirens? Okay. So the other thing that we saw yesterday is gravitational wave lensing. And then there, what we did is solve the propagation equation, and we solve it in the case of a weak field approximation, so that when we are where the lens is not in the strong field regime, which is relevant for astrophysical sources, and then what we found is that our lens signal, we can construct it in time domain from our lens signal in frequency domain. So this is just the Fourier transform that I'm doing here, but just for definitions. And then what we saw, which was the interesting part, is that the frequency domain lens waveform can be obtained from the multiplication of the amplification function, or also known as the diffraction integral, times our original signal that was emitted. And we derive the shape of this diffraction integral that in dimensionless units, W and Y, where Y, this is the source position, angular position, that this is given by this relatively simple integral, where we are integrating over X, which are the angular positions in the lens plane. So I remind you that we have a situation where we have our wave, and then we have our lens, and we have the observer, and then we were in the limiting case in which the lens was thin. So then what we are doing is we are doing a mapping between the plane of the source, where we have positions Y, with the plane of the lens, where we have positions X. And then this was given by the exponential of I W TD, which this TD is the time delay function. This is the time delay, which accounts from a geometric component, which is just the fact that the wave is not going to have a straight line, it's going to be deflected, and then a Shapiro delay, which comes from the fact that this lens has a gravitational potential that is going to delay as well the signal. Okay, so then what we saw is that there are two regimes. One in which the exponent of the exponential is of order 1, and that is what is referred typically as the regime of wave optics, because in this regime, the different paths that the wave could take, they are gonna interfere with each other. So here in this regime, interference and diffraction. So what this means is that the different paths that solve this configuration of the source, lens, and observer, they can interact with each other. And in practice, what it means is that our gravitational wave signal could be, for example, modulated given the interference of multiple copies of the same signal. So this is interesting because what this means is that then you will change the predictions of the waveform compared to general relativity without lensing, and that's something that you can look in the data for. And we will see today, roughly speaking, how you do that. But then there was another interesting regime, which is actually the most common for big lenses, such as galaxies, which is when the frequency times the time delay is a large number, because then the integral can be solved in the stationary phase approximation. And then in that case, what we have is that our diffraction integral is a sum over multiple copies of the original signal. And these copies can have a magnification, as we were discussing in the Q&A. And they will also have some time delay. And they will also have a phase. So this is giving us something which is also quite interesting, which is this give us repeated chirps of the original signal. So this gives us repeated chirps, so we will have something like in our detector, we will detect one signal, and some time delay later, we will detect, well, I didn't do it the best job, but another signal that should have the same frequency evolution, but may have an amplitude which is different, and they are separated by some time delay, and they may have a different phase. So here we have repeated chirps, and here we have distorted waveforms. Yes? Sorry, when the wavelength is small compared to the size of the lens. So what we did is, so this is the equation that defines that limit, so the wave optics. And then here what happens is that you need to solve the integral. You cannot make the stationary phase approximation. And then we didn't go into the details of that, but essentially for simple lens models, actually a few of them only, such as a point mass, you can solve this analytically in terms of hypergeometric functions. It's not really, you can actually do the exercise with Mathematica if you take the time delay surface and then you you choose your potential to be for a point lens, which is just the logarithm of the absolute value of x. This can be solved. But in general, actually, you need to solve this numerically, and it's complicated. But there has been recently, and I should mention that, thanks for the question, that there's been a lot of development actually, and there continues to be a lot of development in defining numerical methods to solve this integral efficiently. So there is a code that solves this now, which I think, in my experience, is the best that there is nowadays, which is GLOW. But there are other people developing methods, so I think there is still work here to be done. Yes? Yes, so what I'm trying to, instead of, so this is, in electromagnetic lensing, this will be referred as multiple images. So in electromagnetic lensing, you will have your lens here, and then you will see one image of the galaxy here, another here, another here. Now, for electromagnetic lensing, for most of the, for galaxies, these are static sources, and you wish to have the resolution to differentiate the different positions of the multiple images. The phenomena is actually the same for gravitational waves, but the thing is that we don't have a good enough angular resolution to see the different positions. So for us, actually, if you look at the sky localization of gravitational waves, we will look for events that cross with each other, and then we say, okay, perhaps if they have a common origin, will be from that intersection. But then the main observational aspect, characteristic that we have is the fact that because these are transients, then the time delay between the signals will make that you will detect one signal, and then sometime later, this can be hours if it's a galaxy, or hours to days, or it can be days to months if it's a galaxy cluster. You will detect another image, and then you could detect another image or another image. So the thing is like they are arriving at different times, but they are actually produced by the same source. Yes. Yes, that's a great question, actually. The question, well, if I understand your question, maybe, I mean, the gravitational waves will be merging in a galaxy. So one could think, okay, the galaxy, I mean, if the gravitational wave is lens, the galaxy should also be lens. But what happens is that, I mean, the possibility to see the lens, the lensing of the host galaxy actually is a bit challenging because for the redshift ranges that we expect the first lens gravitational wave to be, that's actually pretty high redshift. And then second of that is that the gravitational waves are point sources. So they are actually very sensitive to the local potential of the lens. So the predictions from the lensing of the gravitational wave and the lensing of the host galaxy might be a bit different. But potentially, one could have that. The other thing, and just taking the excuse to say that, is that if you were to have a binary neutron star, then in that case, you do expect to have lensing also of the electromagnetic counterparts. So you would expect to have multiple gravitational waves, but also multiple short gamma ray bursts, et cetera, et cetera. And that's something that actually there is a big program that is being built now in what is known as multi-messenger lensing. Yes. Yes. I'm not sure if I am understanding the question. Maybe can you reframe it? Yes. So. Okay. Yes. Yes. So yes. So great. So good point. So the time delay, this scales with the mass of the lens, but the angular separation of the images, this also scales with the mass. I don't know if that's what you are asking, but also scales with the mass. However, still, even if you take like a galaxy cluster, which is the most massive thing that there is in the universe, the angular separation is very small compared to our errors. So I mean, you have to remember that our sky localization is typically hundreds of degrees square. If we are lucky, this is tens of the square degrees. But the angular separation, the Einstein radius, I think is 1 arc second, but I'm forgetting the powers. But if you have a galaxy of 10 to the 12 solar masses, and then cosmological distances of gigaparsec. So you can increase this to arc minutes, but still, like it's very small compared to this. Yes. Yeah, so I will show you a plot later, but I think it's good to anticipate that. So if you, there is some quantity that you can compute, which is called the optical depth. So this tells you the probability that a given point source at a given redshift is lensed via some population of lenses that you are assuming. And if you assume that these are galaxies, then what you have is something which, and we should see later the plot because I don't remember exactly all the numbers. But roughly speaking, I think this is 10 to the minus 2, 10 to the minus, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. So I think redshift 1 is somewhere here. Redshift 2, I mean, we should look into the details, but the main idea is that the optical depth very sharply drops at low redshifts, and then at some point it plateaus at high redshifts. So typically, we would expect the redshifts of where lensing is most probable around redshift of 2, which actually, if you remember the schematic that I was doing for the merger rate history of the black holes, this is expected to have actually the peak around there. So this is in principle where we have more binaries and where lensing starts to be a bit more probable. Something below redshift 1 is quite unlikely just because there are not enough galaxies. Good. More questions? Okay, so I'm gonna now make some, we're gonna do some really basic, but I think still very important derivations or introduction of concepts related to the gravitational wave data analysis. And yeah, which are hopefully help you understand how we are doing our analysis. Yes, so we want to do gravitational wave data analysis. And we will do, as I said, the most basic aspect, but from our gravitational wave detectors, what these detectors output is some data stream, some data as a function of time. And this data will do whatever it does. But what we are going to think is that this data could be decomposed into some noise, n of t. So this is data. It will always have some noise. And then if we are lucky, it will have some signal. So this is the nomenclature I'm going to be using. And then actually, the most important thing to detect a signal is actually to understand your noise. Because for the signals, we have models. And then what we will be doing is asking if our models, once we put when we subtract our model to the data, whether we recover the noise or not. So the first order approximation that one can do is that the noise is approximated, and this we know is not true, but serves for most of the purposes, is the noise is approximated. Noise is approximated as a stationary and Gaussian. And this, of course, you have seen throughout this week random Gaussian fields a lot of times. So hopefully, yeah, this is just another way of writing things. But the nice, as you learn, is that when you have a Gaussian field, then you can just describe it by its 2-point function. And then in the context of gravitational waves, this is referred as the power spectral density. So this Sn as a function of frequency. This is the delta function of 2 frequency modes. This is the quantity that is going to be the most relevant. So the power spectral density. And this power spectral density depends on the detector. I will show you a plot also a bit later. But essentially, it has a shape. Well, as any noise, of course, you detect better at some frequencies, and then you stop being sensitive at other frequencies. For current detectors, this is about a few 100 hertz. And this goes up to about, when this is useful, to 20 hertz currently, and then it can go here up to 2,000 hertz. This noise, yes? No, so that's, well, yeah, so I don't have in my head now an example of what could make that effect. What certainly we know, actually, is that the noise is not stationary. And actually, from time to time, well, actually, every minute, actually, we have some glitches, which is like some transient noises that appear in our data, but that we have learned how to eliminate those glitches. So that's something that violates this. The non-Gaussian features, I think we do have as well, but I cannot give you an example now of what would be generating that. Yes. Yes, and you will see that in a second. Why is that? Yeah. But yes, I stick with my argument that to detect a signal, the most important thing is to understand the noise. Yes. And actually, the noise, what I was going to say is that I don't have time to go into the details. Also, I am really not an expert on it, but it's very interesting that you can understand the shape and frequency ranges of this noise curve from the very different phenomena. So, for example, seismic noise is what is really limiting the low frequencies when you have a detector on the surface of Earth. And that's why, by the way, future detectors such as Einstein telescope, they want to put it underground so that you don't have the seismic waves on the surface of Earth. But then there are these other source of noises you can also understand from actually the fact that your laser also carries some, the photons in your laser also carry some energy. So if you increase the frequency, then you are moving more the mirror. So actually, the more power you have, you also limit that. So actually, people, yeah, develop careers trying to understand that. For us, we will just take the input of what our colleagues have measured in the experiment. And this is all, by the way, public data that one can use. If you want to do calculations, you can take the noise curve of past observing runs and also projections for future observing runs that can all be used. So we have the noise, and then we need to find a strategy to detect this signal. And the strategy that we will have is to filter our data with a given template, so a given waveform that we think could represent a gravitational wave, and then try to see if there is some if there is that shape within the data. So this method is called match filtering. And actually, essentially, what it accounts for is that you take, formally, you filter your data stream. So with a given filter, which mathematically just means doing a convolution of your data with some filter K. Now, something that I don't have time to do now, but you can look in the notes, is that the optimal filter, and this is actually not very surprising, but if you have some data which contains some noise and some signal, the optimal filter is actually one which is parallel to the signal. So in the sense, parallel in the sense that you have to the signal, you have a filter that in frequency domain is proportional to the frequency domain signal divided by the, weighted by the power spectral density. And this notion of being parallel actually comes from the fact that you can define some inner product for some real functions of time, A and B. You can define this inner product as 4 times the real part of the integral from 0 to infinity of the frequency of the complex conjugate of the frequency domain's signal times the times the Fourier transform without the complex conjugate of the other one, weighted by the power spectral density. So this is a noise weighted inner product. And then what you see is that you can do this derivation, and looking from the notes, is that actually you can rewrite this in terms of an inner product, and then the maximum signal would be when they are parallel. And what this allows to define is the signal-to-noise ratio, which is essentially just saying what the name is. Signal-to-noise ratio is telling you how large is the signal compared to the noise, and this is something that the signal-to-noise ratio square, SNR square, which in the gravitational wave community is called mostly as rho square. This is equal to the our gravitational wave inner product with itself, which is just 4 times the real part, and then is the same as before, but because we have the signal with itself, then we just have the amplitude square. So this is the optimal signal-to-noise that one could obtain from a signal. And this is also a way in which you can address the detectability of a signal. So typically, but this is not how we do it actually in LIGO and Virgo and Kagra, but it's an estimation but you can say that in a single detector, a detection would be when your signal to noise is larger than some threshold, and typically used threshold is that this signal to noise is 8. And this comes also from the fact that you can relate this signal to noise ratio to some probability, false alarm probability. But what this means is that here you have a procedure. If you have, for example, you want to understand if a given signal is detectable or not, you can compute you have your waveform model, h of f, and then you have a detector sensitivity that was given to you, and then you compute this integral and ask whether your signal is above or below the threshold, and this will give you a sense of whether this is detectable or not. Is this clear? Yes. Yes. Exactly. Yes. Yes. So this is the optimal because you are assuming that you have the signal with itself. Yes, exactly. So in practice, when we are filtering the data, what we do is that we have a whole family of templates that we pass over the data, and then we see which templates give the maximum signal to noise. But with this, for example, what you can do is, because you know that the signal is inversely proportional to the luminosity distance, so you can compute, for example, this horizon distance, which tells you how far you could detect a signal. If you compute the optimal signal to noise for a luminosity distance of 1 megaparsec, and you divide by your threshold, that you can say this is 8. And then this will give you the distance in megaparsec for how far you can detect a gravitational wave. So this is known as the horizon distance. So for a given, depending on the mass, and we will see some plots of this, and you, of course, you can relate horizon distance to horizon redshift, assuming a cosmology. So typically, one has the horizon redshift looking something like this, where you have some peak for current detectors, where this is the total mass. This is about 100 solar masses. And now you can understand the shape of this horizon distance. That's because the horizon distance comes from the signal to noise, which comes from the ratio of the amplitude and the noise. So the amplitude, we saw that the H was proportional to the redshifted the shear mass to the 5/3. And then we have also this sensitivity curve. So this tells you that you are mostly sensitive at 100 Hertz, which is also more or less, so where you have the chirp of signals of tens of solar masses. But yeah, essentially this is telling you this is the low frequency noise, and then this is the high frequency noise. Yeah, so the fact that we detect differently at different masses is a combination of the fact that the signal scales different with the mass, and that our detectors are sensitive differently to different masses. Is this clear? This is, of course, very important for cosmology because that determines how far you can see a signal. And actually, something that I will point out, but well, let me do it now, is that actually when you go to the regime of compact objects of a solar mass or so, these are really, really low redshifts. So binary neutron stars, we can see essentially to distances 10 times or even more smaller than what we can see binary black holes. That's another reason, by the way, why we are detecting mostly binary black holes, because we can cover much more volume. So the number of detections, roughly speaking, will be proportional to the volume that you see, and this will be proportional to, roughly speaking, to the horizon distance cube. So if you can see a bit further, and this horizon depends on the mass, so you can really get many more events. This, of course, also, if you also to connect everything, if you were to have some magnification, this will also go directly into, will change as well your horizon distance. Yes, is this clear? Yes. Yeah, so it really depends on the magnifications that you have, but what we expect for the first lens signals to have is magnifications of around 10, because we need to have them actually quite magnified in order for them to be within the horizon of our detectors. So then you are, essentially you will be going in distance like a factor of 3 farther away, more or less. Okay, so there is another, well, maybe just say it quick. I will say it quickly. I think another element of data analysis, to do like quick calculations, which is useful, is the mismatch. So if I want to quantify the difference between two waveforms, H1 and H2, something that I can do, I can create a statistic, which is the match, which is simply the normalized inner product of both of them. And this, sorry, this is 1, 1, and 1, and this is 2 and 2. So the mismatch, epsilon, sometimes referred as epsilon, is 1 minus the match. And this is something that you can, is a way that you can use to quantify difference between waveforms. But actually, what I want to spend a bit of time before going to the slides is explain very quickly the main idea of how we do parameter estimation. And the main idea is actually very simple, is that if we think that there is a signal in our data, and then we have we have a model. So we have a model h of t that depends on some parameters. And we think that h of t describes some signal s of t that we think there is in our data. Then what we can do is that we can look, the way we do parameters is we look for the parameters, the parameters theta, such that when we take our data and we subtract this model, then what we obtain is the noise. So if you have something that is representing well the signal, then when you subtract it, you should get the noise. And then how do we know if we are properly characterizing the noise? Is because the noise is a Gaussian random field in this approximation. So the distribution of the noise should follow actually a normal distribution, which is with the notation of this noise-weighted inner product is simply given by this. So when we do data analysis, actually, this is the likelihood that we use when we use Bayesian inference. So yeah, so the likelihood for Bayesian inference, and sorry also that I don't really have time to explain in more detail the really nice properties of statistical properties here. But essentially, what we, yeah, how can I say this? Yeah, so essentially, this is going to be the likelihood that is describing our data, and then what we need to do, we need to just, instead of writing the noise, what we have is that we have some data minus model and data minus model divided by 2. And this we can, this is also defined as e to the, I guess, lambda. So this lambda is the, log lambda, the log likelihood. And then the log likelihood in this case will be coming from this inner product that you can expand, and you will get the data inner product with the template, and then you would get minus 1/2 of the template with itself. And then you will have minus 1/2 of the data with itself, and then you could have some constants. Notice here that these first terms depend on the parameters theta, the second term depends on the parameter, but this third term that hopefully you can see from the back as well also is a constant. So actually the only terms that we care about are the first 2. And then if you use Bayes' theorem, what you can construct is the posterior distribution of the parameters given the likelihood that you observe some data with your model. So if you use Bayes' theorem, and for those who have not heard about it, I recommend also Wikipedia is useful here. No, but essentially, you want to compute the posterior distribution of some parameters given the data, and this is going to be proportional to this function that I will explain in a second, times our likelihood. So, and then I'm not considering here the terms which are constant because I'm taking here to this to be proportional. So here we have the posterior. So this is what we want to infer posterior distribution of theta given the data that depends on our prior assumption, prior distribution of theta, that this could be something that is an informative, this could be something that we say, okay, just we don't have any idea of what would be the parameter, this is flat, or it could be something that is informed by previous data. And then this is giving you the likelihood of the data given the model h of theta. So if you want to obtain this posterior distribution, then essentially what you need to do, thanks to Bayes' theorem, is just maximize your likelihood, find the parameters that will give you the maximum likelihood, and then you need to multiply by the prior. Yes? Is within here. Because this is, so I'm saying theta, but this is actually the set of parameters that we have seen, that these are the masses, the spins, the et cetera, et cetera, et cetera. So one way actually of seeing the covariance actually directly is in the limit of very high signal to noise. And that will be the last thing before the slides. So in the limit of high signal to noise, actually so typically one would have a posterior distribution for some parameter theta I as something that could be non-Gaussian, very broad, but we want to focus to the case of high signal-to-noise ratio, in which this will be some nicely distributed narrow Gaussian. So in this case, what you can do is that you can take this expression and you can expand around the maximum likelihood. So we expand around the maximum likelihood, which is defined as the places where the likelihood, the first derivative of the likelihood vanishes. And then what this means in the high signal to noise approximation is that the posterior distribution would be proportional to the exponential of -1/2 of some matrix gamma ij times the error theta I, theta j. So we are doing the expansion around the maximum likelihood, but and then what this, because the maximum likelihood, the first derivative vanishes, then it's only the second derivatives that come into play. So this element here, this is what is known as the Fisher information matrix. And notice here as well that we have assumed flat prior, but actually in the limit of high signal to noise, typically the prior is very large compared to our observation. So that's fine. So then the covariance matrix, Cij, will come from the inverse of the Fisher matrix, which is just theta j. And the the Fisher matrix, gamma ij, would be given by taking, so this is the maximum likelihood is the first derivative of this expression. We have to do the second derivative of that expression to get the Fisher matrix. So we get a second derivative of the parameters I, j. So here, I is defined as derivative with the parameter theta j. Sorry, I with respect to I. And then the expression you get is h minus s. And then you have plus partial derivative of I, and then partial derivative of j. So this is what you obtain. But then what you can notice is that in the limit of so this term here is proportional to the noise, n, which is going to be much smaller than the signal in the limit of a high signal to noise ratio. So actually, to compute the Fisher matrices, what you can do, you can approximate this by this second term only. Okay, and then what you can show, actually, and this I will leave as an exercise, is very simple to do, is that, for example, if you have the simplest model that you can imagine, which is just if you have a gravitational wave that is described by two parameters, an amplitude and a phase. Actually, you can very easily compute the Fisher matrix because the derivative of h with respect to the logarithm of a, this is just h, and the derivative of h with respect to phi, this is simply I times h. So taking that into account, you can realize actually that the Fisher matrix for this model is diagonal and is actually proportional to the signal-to-noise ratio square, which means, I didn't say that, but I guess so this is the covariance matrix. The diagonal elements are the variances. So you can see that the variance of the logarithm of A is equals to the variance of the logarithm of the phase, which both scale inversely with the signal-to-noise ratio. So what this means is that, roughly speaking, of course, in general, there are more parameters that will be degenerate with each other. But roughly speaking, for example, the error in the luminosity distance will scale. The relative error in the luminosity distance will scale with the inverse of the signal to noise. and the errors in the phases will scale with 1 over SNR. And the error in the phase can be related actually to the error in the shear mass, but that's something that we don't have time to go here. So I went very quick, but hopefully you are getting a sense. I hope there are some questions. Yes. Yeah. So sorry that I'm taking the opportunity to start putting this. So the case of LISA is actually very different because LISA will be an instrument that will be dominated by the signal and not by the noise, as you are pointing out. So what this means is that in the LISA data stream, so in this data stream, there will always be some signals. And those in particular, for example, will be the background of source of galactic binaries. This will make a background that will cover some frequency range. So then what happens there is that you cannot take the approach that I'm doing here of thinking of each signal independently of each other. So here, this is a model that describes the data where there is only one signal. In LISA, you will need to simultaneously analyze multiple signals. The way that this is envisioned, but this may also change if better methods are developed, is that you iteratively infer. So you first infer the properties of the loudest signals, and then you continue with the next one, and then what you do is that once you have done a first round, you do it again. So you analyze again the loudest signals, but having taken into account that there were other signals in the data as well, and you repeat the cycle multiple times until you converge to some result. What this will mean actually in practice, which is also very different from LIGO, is that in LISA, you may detect a supermassive black hole binary the first day that you put the detector, and with that, you will infer some masses. But actually, a year later or 2 years later, you will know so much better the instrument and the sources within the instrument that actually you will improve or it might change the actual value of the mass that you infer in the first event. While now we have data and that, we improve the waveform models, and that may change what we infer, but not in a large way. More questions? Sorry, where? Yes. Yeah, so that depends on the regime you are. So, for example, if you are in the regime of wave optics and your lens is described by a point lens, then you will have two extra parameters: the mass of the lens and the impact parameter. If you are in the regime of multiple chirps, then the number of extra parameters will depend on how many extra chirps you have. And for every pair of events, you will have a relative magnification, and you will have a time delay, and a phase, sorry. So three parameters per pair. Yes. More questions, yes. Yeah, so, sorry, can you? Yeah, no, yeah, it's because that, exactly, yes. Yeah, yeah, that's true. And then I think also the other important thing to have in mind is that, yeah, you may have like a very large noise and then very small signal, but when you filter this data with a model, you are going to accumulate signal to noise throughout the whole spiral. So actually, this allows you to detect signals which are whose amplitude is smaller, because if the longer they are, the more signal to noise you accumulate. And therefore, you can have more better observation. You can detect signals as well, despite they being smaller. So something, yes. 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 So you use a template to extract the signal, but then the question is, how do you know if the parameter, if this template is describing the data, the signal properly? And one way of doing it is by saying that, okay, if I'm doing this properly, my model describes properly the signal. Once I subtract this model from the data, I should just have noise. That's the only point. And that's useful because if you are in the, so why people do this? Because if you assume that the noise is Gaussian and stationary, then you have a likelihood which is very simple. So your likelihood, this Gaussian likelihood is super simple. And that's the advantage, that you have a well-defined likelihood where you can look, where you can see the parameters that you are obtaining. Yes. Yes, the noise is, yes. Yeah. Yeah. So the one thing that is important is that it maybe is not highlighted in this toy example, is that here, in general, you have these 15 dimensions at least. So these parameters will be correlated with each other. And that's something which is important. So, oops, this, here. Yes, so well, this is the signal that we have already seen. These are the sensitivity, thank you. This is, for example, for the LIGO detectors during the time of observation of the first event. You see here, this is the strain noise, which is related to the power spectral density. And you see this is the typical shape that you have. There are many things here which, well, are not so relevant, but the important thing is that where we measure best is around 100 or 200 hertz. And then the points that I want to emphasize here is that the parameters that we infer are actually can be correlated with each other. And in particular, we have derived in this course that the parameter that we measure best is the shear mass. So actually, when you look at the data, so this is again for the first event, these are the masses that we infer for the primary mass and the secondary mass. So actually, the shear mass is this direction which is perpendicular here. So the direction that you best constrain is essentially the shear mass, and then the other one is essentially the relative the mass ratio. But parameters can be correlated with each other. And actually, when you include more parameters, this is again for the first event. You see, for example, here, this is the shear mass. The shear mass is very nicely constrained. So it has an error of about 1 solar mass, which I guess, well, it will be mostly here. But then, for example, you can have other parameters which are highly correlated with each other. And in particular, the skylock position, the right extension, and the declination are degenerate with each other. And you can also have the phases degenerate. But in general, actually, what one has for every event is something like this, where you have these 15 parameters that describe your signal, and you see that many of them are correlated, some which are important for us, where we have this. So this is inclination, and what is distance? No, we don't see here. Sorry, where do I have the... These plots are always a bit confusing. No. Sorry, can someone help me? Where should I want to see the correlation of Jn, theta Jn, with the distance, which is it's not so correlated here. Okay, maybe we'll see a better example later. But important, you see masses correlated. You see here distance and sky position. Yeah, many parameters can be correlated with each other, so it's not always so easy well, one needs to take into account that the model has a lot of elements. Is it clear how to read these plots, more or less? Or what this is doing, I should have said, is doing, you are taking your posterior distribution, which has whatever number of dimensions, and then you are looking at the slices of a given plane of parameters. And these plots here in the diagonal, these are the one-dimensional distributions of each parameter. So with the two-dimensional part, you see correlation between parameters. With the one-dimensional, you see the errors that you have. So this is for the sky localization of the binary neutron star event. And this is to emphasize something that I said already in the colloquium, but the fact that here in this case, actually the blue line is what was, this blue and this blue is what was found with the two LIGO detectors, but thanks to the fact that Virgo was online, the sky localization was reduced to this green area. So having multiple detectors is quite useful in terms of finding signals, because then what you do is you have a much smaller region to cover with your telescopes to find information of the, to find evidence of the transient and the host galaxy. Here it is. So for the case of 17017, this is the posterior distribution in the Hubble parameter, together with the posterior in the plane, sorry, of the cosine of the inclination. So what you are seeing here at play is precisely this degeneracy between distance and inclination, because from the distance, in fact, for this event, the error in the redshift we can consider as negligible. So from the distance, we have actually direct information given the redshift of h0. So therefore, what you are seeing is that there is this large degeneracy with the inclination. So actually, something that we didn't mention in the course is that if you have an electromagnetic observation and you have a good model for your electromagnetic observation that allows you to infer, for example, that you know very well, you say, okay, I have this model for binary neutron star mergers that predict that the viewing angle should be such and such, because I've observed the signal with this and this other observation. That's actually useful, because then you can put that prior from the electromagnetic observations and help improve the constraint from the gravitational waves, which is can be degenerate here. And this is also to give you a sense of how it looks the case of dark sirens. This is for the first binary black hole that was observed with LIGO, Virgo, the two LIGOs and Virgo. This was in August of 2017. And then this was the sky localization region of the event. And then what you are seeing here, this is a map of essentially the mass that in the DS catalog in the sky localization, but also in terms of redshift. And here I don't. Yeah, I'm not sure if these white lines correspond. Yeah, I'm not. I forgot actually for this event how it looks the redshift distribution, the luminosity distance. But well, what you would need to do is to look for the galaxies within this error box, which are consistent with your event. Okay, so just so that you see at least once, and you can go and look at these plots in more detail later. But this is actually the best of our knowledge in terms of what is the mass distribution of binary black holes given our last catalog. This is something that soon will be improved because there will be, we will be doubling the number of events. But essentially, this is a busy plot with different models. But what you should get at is that essentially what the data is telling us is that there is a peak in the mass spectrum of black holes at around 10 or a bit smaller masses, and then the mass spectrum decreases, and then there is another peak at around 35 solar masses, and then the mass spectrum decreases significantly. Notice here that the vertical axis is in logarithmic scale. So actually, it's much less probable to have events here than events here. Now, if you look at if you do what I told you of getting the alerts in your phone, well, actually, you cannot do that because you don't have the information of the mass. But if you were to look at the masses of the events that we observe, you will say, okay, but we are observing many more events which are 40, 50, 60 solar masses than events which are 10 solar masses. But you need to remember that the sensitivity that we have is much larger for binaries which are more massive. So actually, when we are inferring the source properties, we are taking into account that we know that there is some selection bias, that we are more sensitive to more massive things. So that's why, despite most of the events being in this range, we know that actually in reality there is many more events here. And what this means in other words is that actually when you think of future detectors, we'll be able to see very far for all the mass ranges essentially, that actually most of the events will be lower mass black holes. And then you can say, okay, what about even lower masses? And this is, again, a lot of models, which it doesn't matter the detail, but this is the inference of the mass spectrum of all the low mass binaries. So this is without making distinctions between binary neutron stars and binary black holes. And what you find is that it seems that at low masses, where you expect only to have neutron stars, that the merger rate is actually higher. Then it decreases, but then actually later it's not so clear if it will decrease even more or it's just constant. So this is actually something which is actively being researched. But what is you can see here is that in principle, the rate of neutron stars or for most of the cases, the rate of the neutron star should be larger, significantly larger than that of binary black holes. Although, if you take the lower part of this distribution, it might be that it's not so different. So but we do expect the binary neutron star to be at least a factor of a few larger than that of binary black holes. Okay, and this the other piece of data is the merger rate history. So this is our inference in how many mergers, how many binary black holes are merging as a function of time. And then this has large uncertainties, but what the main takeaway here is that we have already evidence that actually the merger rate is increasing as a function of redshift. So this merger rate has a slope which increases, which is something which is consistent with the picture that I was telling you of these black holes following something which is similar to the star formation rate. Actually, the star formation rate curve, curiously enough, fits very well the median, but you shouldn't read too much into that. But the important thing is that we have evidence that this is growing. So I think I had a bunch of more things, but I will put the slides on the repository so you can have access. But maybe I just want to finish with giving you actually constraints, current constraints on the Hubble parameter for the different standard siren methods. So here, what so 17 is the only event in which we have been able to use the bright siren method, and is this line over here. And then the dark siren here is this dashed line in orange, which has larger uncertainties. And then the spectral siren method will be this dotted line over here. So a few lessons from this plot. First is that 17 is the best one of the three methods so far, but actually already the others are getting closer. And then the other thing that you can notice is that actually the dark siren method is slightly better than the spectral siren, but not so much. And actually that comes from the fact that actually implicitly most of the information of the dark siren method is coming from the fact that this plot was fixing the mass spectrum. So you were actually, most of the information actually is from the population inference. And this is shown in this plot over here, where the best fit astrophysical model was fixed in the orange line. But then if you take other priors, actually you get things which are very different. So this comes to the question that we had yesterday, that indeed, I mean, what you need to do if you want to do this properly is that you need to do the spectral siren together with the dark siren. So you always need to infer the population. Yeah. So this is something that I saw before, but now that we know how to compute this horizon redshift, perhaps is more meaningful, and you see that indeed at low masses, the horizon redshift is really, really much smaller, and it's only when we go to next generation detectors that we will be able to detect, for example, many binary neutron stars. But still with current technology, it's going to be only very nearby neutron stars that are going to be detected. So when you have time, later you can see the slides and see, for example, predictions for the expectation of the accuracy with Einstein telescope for bright sirens, with different methods, and then also for dark sirens, depending on the different networks, and also for spectral sirens. But I think it's best to stop here, and if there is any remaining question, I will love to answer it. Thank you so much.
Okay, questions for Jose? Yes.
I love your energy, Rogerio. It's inspiring.
Thanks, Jose. Is there any way of like predicting the effect that a lens will have on the gravitational wave from, we'll say, the optical lens of a potential host galaxy? From the image of a host galaxy, we'll say.
Yes, so if you fix and this is something that is also in the slides, if you fix, for example, your model to a point length, then you know how the waveform is going to be distorted. If you have another lens model, you can have like NFW Navarro-French-White halo. You could solve the diffraction integral, and then you could get distortions to that model as well. Yeah, so you need to fix the model, and then you could obtain that.
Thank you.
Yeah.
More questions for Jose? I don't see any hands, so let's thank Jose for this very nice set of lectures.
Thank you so much.
So it was a very intense week. Next week will be even more intense, or as intense as this one.